So recall that a system of m linear equations in n variables is written in this form. So I have a11 x1 plus a12 x2 plus a13 x3 up to a1n xn equals to b1, a21 x1 plus a22 x2 plus a23 x3 plus a2n xn equals to b2, a31 x1 plus a32 x2 plus a33 x3 all the way up to a3n xn equals to b3. We continue in this manner up to am1x1 plus am2 x2 plus am3 x3 plus other several terms amn xn equals to bm. So this is what we call a system of m linear equations in n unknowns. So b1, b2, b3 up to bm are just constants. So let's call this 1. Let's call that system 1. So we can rewrite 1 in matrix form such that the coefficients aij's occupies one matrix, and then the variables x1, x2 up to xn defines another matrix, and the constants b1, b2 up to bm occupies another matrix. So 1 can be written in matrix form as so what you do, you write all the coefficients as one matrix, multiply by all the vectors, all the unknown values x1, x2 up to xn, and then you equate to the vector of constants. So this is what you write. So a11, a12, a13 up to a1n a21, a22, a23 up to a2n, a31, a32, a33 up to a3n, all the way up to AM1, AM2, AM3, up to AMN. You multiply this by X1, X2, X3, all the way up to Xn is equals to B1, B2, B3, all the way up to Bn. So when we write 1 in this form, then we say that we have described system 1 in matrix form. So this is called coefficients matrix. So this is what we call coefficient matrix. This is what we call variable matrix. This is what we call constant matrix. There's still another way of now rewriting system 1 in such a way that the only things which matters are the constants matrix and the coefficients matrix. But then you separate the coefficient matrix and the constant matrix by either a straight line or a dotted line. And when we arrange system 1 in that way, we say that system 1 has been written in augmented form. So you see, the way this structure is arranged is of the form, there's a matrix A, and then there's a vector X, and then there's a constant vector B. So that in matrix form, any system of linear equations can be written as AX equals to B, where A is the coefficients matrix, X is the variable matrix, and B is a constant matrix. So the matrix form of a system of linear equations produces an equation of the form AX equals to B, where A is a coefficients matrix, and say coefficient of coefficients matrix, X is the variable matrix or variables matrix, while B is what we call constant or constants matrix. can say vector, vector. So any system of M linear equations will take this structure. Now, when you take the coefficients matrix, you join to the constants matrix, and you form one matrix such that the coefficient matrix and the constant matrix are separated by a line, either complete or dotted. You form what we call an augmented matrix. So when the coefficient matrix and constant matrix are joined, separated by to form a single matrix. Or you can write it as A, then you dot the line. So I mean, you can either use a straight line, or you can use a complete solid line. You can use a straight line which is complete, or you can use a straight line which is dotted. Then this matrix an augmented matrix of the system. So when you pick all the coefficients matrix separate by a line, write the constant matrix, then that new matrix is called augmented matrix. So for system 1, the augmented matrix will be so I have A11, A12, A13, up to A1N. You separate by a line. Remember, you can either make the line straight or you can make it dotted, whichever case you pick. So A21, A22, A23, A2N, A31, A32, A33, up to A3N, A M1, AM2, AM3. So this is B1, B2, B3, all the way up to Bm. So this is what we call the augmented matrix of system 1. You can either decide to make this a dotted line or a complete line. All of them are accepted. So to create this augmented matrix for any given system, the first step is to know how many variables are involved in the system of linear equations that you are given, and then rearrange the equation such a way that in each equation in the system, we have uniform starting variables, second variables, third variables, up to the last variable. So if the equation has x, y, and z, then you ensure that if you decide that each equation should start with an x, then ensure that all of them are starting with x. If you follow by y, then all of them should also be followed by y. If you want to finish with z, then in each of the equation, then the last variable must be z. And then in some equations whereby all the available variables are not used, you replace the positions of those variables by zero coefficients, because zero coefficient doesn't change the structure of the equation, so that you take care of each position of the coefficient in the whole system. So as an example, I want us to start by changing a system into matrix form, and then changing the same system into augmented matrix form. So let me call them appetizers. Change the following systems into one matrix form, two augmented form. So as usual, we make the first case to be an easy case, x plus y equals to 3, and 2x minus y equals to -5. And then b, 3x plus 4y plus 6z equals to 10, x plus 3z equals to 0, y minus 10z equals to 13. So let's begin by this. What was the coefficient for z in this case? Okay, let me say 5. So good. So the first system involves how many variables? This first system has how many variables? 2, correct, X and Y. So, and likely enough, the first equation starts with X followed by Y. Similarly, second equation starts with X followed by Y. So coefficient of X in the first equation is number before X, 1. Y is also 1. X in this case is 2. Coefficient of Y in the second equation, -1. So this is the matrix of coefficients or coefficient matrix. And then in this system, the starting variable in each equation is X. So you write it here, followed by Y. You write it down here. Equals to the right-hand side. This is 3, followed by -5. So this is what we call matrix equation. So this is for part A. Then augmented form of matrix. Remember, it is given by, so remember, this is our A, this is our X vector, and this is our B vector. So augmented matrix is A, then B. So once we have the matrix equation of the system, it's very easy to write the augmented matrix or augmented form by simply picking the coefficients matrix, separate by a line, write the constant matrix, and then write it as one complete matrix. So this will be 1, 2, 1, -1, separate with a line, then B is 3, and then -5. So that's what we call augmented form or matrix of the given system. Now, for the second case, how many variables are involved in that system? 3. So you write each of the equations such that there's always a position for all those 3 variables. So this is the same as 3x plus 4y plus 6z equals to 10. Next, we have x. Now, the second equation has no y, but you force it there by making the coefficient of that variable which is missing 0, and then plus 5z equals to 0. The third equation has no x. You force it there by making its coefficient 0, plus y minus 10z equals to 13. That's the first thing. Know how many variables are involved in the system, and then rewrite the system such that we'll have uniform starting variables, second variables, third variables, etc. And in case there's an equation that doesn't have any of the variables under consideration, force those terms by making coefficient of those missing variables, 0. So once you have that, it becomes easier to write the matrix equation. So from the first equation, coefficient of x is 3, y is 4, z is 6. Then we have 1, we have 0, 5, 0, 1, minus 10. This is 10, this is 0, and then this is 13. So this is the augmented matrix or augmented form. But then the matrix equation for that system will be 3, 4, 6, 1, 0, 5, 0, 1, minus 10. And then the way the variables have been arranged, x is the starting variable, y is the second variable, z is a third variable, and then constants 10, 0, 13. So that's what we call the matrix equation. Now I want you to try to write this in both matrix and augmented form. The system is 3x1 plus 2x2 minus x3 plus x4 equals to minus 1, 2x4 minus x3 plus 2x1 equals to 0, 2x3 plus x2 plus 3x1 plus 5x4 equals to 2. Can you try to write the matrix form of that system? Are you able to do that problem? So in this case, you realize that now in our system, how many variables are available? 4. So x1, x2, x3, x4. So you first start by rewriting the system. So equation 1 is 3x1 plus 2x2 minus x3, and then plus x4 equals to -1. And then how should I rewrite the second equation? Correct. Because now, remember, we have to have uniformity the way we're writing our system. So if the starting variable is x1, all the equations should be starting with x1. So I'll have 2x1 plus 0x2 because there's no x2 minus x3, and then plus 2x4 equals to 0. Third equation, x1 plus 2x2, or just x2. X2 is just having coefficient 1. And then x2 plus 2x3 plus 5x4 equals to 2. So that's the first step. So then now it becomes easier to write the matrix equation. So just pick the coefficients. So we have 3, we have 2, we have 3, we have 2, we have 0, we have 1, -1, -1, 2, 1, 2, 5. And then we have 4 variables, x1, x2, x3, x4 equals to -1, 0, 2. So that will be the matrix equation. Then augmented form is simply given by A, B. So which will be 3, 2, 3, 2, 0, 1, -1, -1, 2, 1, 2, 5, then -1, 0, 2. So that's how we write the augmented form of that system. So the first thing is to count how many variables are available, are used in the system, and then rewrite the whole system such that there's an order in which the variables are following each other in each of the equations. For variables which are missing in some equations, replace their coefficients by 1, by 0, and then write the matrix equation, and augmented matrix can always be easily extracted from that rearranged system. So some definition. A system of linear equations which has at least one solution is called a consistent system. So a system that has at least one solution is called a consistent system, while a system of linear equations which has no solution a system of linear equations which has no solution at all is called an inconsistent system. So before we discuss how to find solution of a system and determine whether it's consistent or inconsistent, it should be noted from the start that any given system of linear equations, for any given system of linear equations, three things are possible. One, the system can have exactly one solution, what we call a unique solution, or the system can have an infinitely many solutions. And the last case is that the system can have no solution at all. So any given system of linear equations will lie in any of these three categories, either one unique solution, either unique solution, many solutions, or no solution at all. Any solution of n linear equations in n variables one, the system has exactly one solution. A unique solution. Number two, the system has an infinite number of solutions. Or the system has no solution. So if a system lies in case one, has exactly one solution, is that consistent or an inconsistent system? Consistent, because there's a solution. So this is consistent. So if it's taking case one, then it can as well be described as consistent. If it has an infinite number of solutions, consistent or inconsistent? Consistent still. If the system has no solution, inconsistent, correct. So that's what we have. So before we start discussing different methods of solving systems of linear equations, it should be known to you that a system will either take any of these three cases. There's a solution, there is no solution, or there are many solutions. So there's what we call elementary row operations. So these are simply the operations which we mostly use on systems of linear equations to enable us to transform the system into a more easier system to solve. So I'll state them, and then thereafter we'll see how to a specific case. So one, we can interchange so listing elementary operations with respect to system of equations, but the same things will be applied when you are referring to simply a matrix. So the first case, interchange two equations. So you can interchange two equations to see how you can convert a system into an equivalent system that is easier to solve. Number two, you can multiply one equation by non-zero scalar. Number three, you can add a multiple of a row or simply add a multiple of one equation to a different equation. So those are what we call the elementary operations with respect to equations. But you can also state the same operations with respect to a matrix. The same things works. One way of doing operations on matrix, you can interchange rows. Number two, you can multiply one row by a non-zero scalar. Then number three, you can add a multiple of one row to a different row. So those are the main row operations in a matrix. So we want to define what we call row echelon form or row echelon matrix and reduced row echelon form or reduced row echelon matrix. Row echelon form or row echelon matrix. So matrix is said to be in row echelon form if it satisfies the following conditions. So any matrix that satisfies these conditions that you are going to state is said to be in row echelon form. So the first condition, all zero rows if any, are at the bottom. Please get the condition clearly. All 0 rows, if any. So sometimes the matrix need not to have 0 rows. But if there's any row that has all the elements in that row to be 0, then it must be at the bottom of the matrix. Then the next property or the next condition, the first non-zero entry from the left in each row is a 1. And this one is called leading 1. So any non-zero row means that at least in that row, there's a position that has a non-zero value. Then the first number must be 1, which we call leading 1 for that particular row. And the last condition, each leading 1 is to the right of all leading 1 leading ones in the rows above it. This is what I mean. Like if I have 1, 0, 0, for instance, in this matrix, so the condition 3 says that each leading 1 is to the right of the leading ones in the rows above it. So this matrix has only 3 rows, And so that third condition is referring to when we are in this second row, because this is the only row that has non-zero elements, whereby we can do the comparison with what is above it. So this 1 is to the right side of the leading 1 of row 1. You see, this is row 1, this row 2, this row 3. So this 1 is to the right with respect to this leading 1 on the row above it. So if a matrix is already in row echelon form, and in addition, each leading 1 is the only non-zero entry in its column, then it is called it is said so when a matrix satisfies all the conditions for row echelon form, and in addition, for every leading one, that is the only non-zero element in that column, then such a matrix is called reduced, or is said to be in reduced row echelon form. So row echelon form matrices So row echelon form matrices have this particular structure. So we might have 1, 1, 0, 1, then 0, 0, 1, 0, 0, 0, 1. So this may be 0, or may be any other non-zero number, etc. Such that there's this way in which the leading entries behave, or the leading ones. Not all matrices will produce this, but the idea is that we'll always have this kind of a stair, such that once we have a leading one in any given row, then all the elements below the leading ones are 0. And we have this structure. Or even we may have this 0, 1, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 1. This might be also another structure of a row echelon form matrix, where this is the leading one. We have another leading one here. Remember, the leading one does not necessarily mean has to be 1 from the start. It can be actually along the way, like in this second case. This can be any other number. It can be 0 or non-zero numbers. Now, if you are to convert these matrices I've drawn here to be in reduced row echelon form, then you ensure that all those stars or all those x's I've drawn in the staircase are zeros, such that any row that has a leading one, that column will only have zero element. So when you change everything here to be zeros, then you produce what we call reduced row echelon form or reduced echelon form of the matrix if you change all these spaces to zeros. Small break, and then we come back to explain to classify matrices as either being in reduced row echelon form or in row echelon form or neither.